So in order to perform buckling analysis on that crankshaft, I have opened Ansys Workbench and I'm going to drag and drop the static structural. Once I drag and drop the static structural, I'm going to also drag and drop eigenvalue buckling, and I'm going to just drop it on the solution cell of the static structural. As this particular crankshaft has been prepared by structural steel, we need not change any material. So I'm going to right click on the geometry cell and go to import geometry, go to browse, and I'm going to select the crankshaft. Then I'm going to double click on the model cell in order to open Ansys Mechanical. So once this Ansys Mechanical is open, as this is a coupled analysis, we are going to have access to these two systems. So one is the static structural system and another one is the eigenvalue buckling system. So now what I need to do is I need to change the units to this US customary, and once I have changed the units to US customary, you can just say right click on static structural, say insert, go to this fixed support, and you need to fix this particular face as well as this particular face, and I'm going to apply. And once I have applied these constraints, then I'm going to right click, say insert pressure, and I am going to select this particular two faces, and I'm going to say apply, and I'm going to apply a pressure of 300 psi. So I'm going to just enter 300 psi. So once I have entered the required value, now what I need to do is I need to solve this particular problem. Now here, instead of finding out two modes, I want to find out 4 buckling modes of this particular crankshaft. For that purpose, what I am going to do is I am going to go to the analysis system in the eigenvalue buckling, and here I have an option known as the maximum modes to find. In this, I am going to set it to 4. By default, this will be set to 2, so that if you are going to leave it to default, you are going to find out 2 buckling modes. And once I have changed this particular value to 4, I am going to just select 2 systems and just click on solve, so that what happens, the static structural will be solved and then eigenvalue buckling will be solved. So once the solution is done, I am going to click on the solution branch, and here I am going to find out the load factors or load multipliers. See here, instead of 2 load multipliers, I was able to calculate 4 load multipliers. This was because I have changed the analysis setting and asked the computer to find 4 buckling load factors instead of 2 buckling load factors. In general, we can calculate any number of buckling factors, but what happens if the particular body is subjected to the first buckling mode, it is going to fail. And if we want to study the further behavior, it is known as a post-buckling analysis. Coming to the values here, we have both negative load multipliers as well as the positive load multipliers. So if you want to find out the buckling load, what are you going to do? You are going to take the value of the applied pressure here, and then you are going to multiply with this particular load factor, and then you are going to get the value of the critical buckling load in mode 1. Likewise, if you are going to multiply the pressure value with this one, you are going to get the critical buckling load in the mode 2, likewise mode 3 and mode 4. So then coming to the positive values as well as negative values. So what happens? A negative buckling factor means that the particular structure under consideration will fail if the load direction has been reversed. So for example, instead of say applying this particular load in this direction, if I change this direction, then what happens? This structure is going to buckle in mode number 1. So if I reverse this direction, let us say instead of applying like this, if I just apply it towards the outside, this particular structure is going to buckle. Likewise, see, getting a negative buckling factor is not a error. It is always possible. For example, if you take pressure vessels, if you take water storage tanks and other sorts of examples, you may have lot of number of negative buckling factors. So what happens is, it is up to the CA engineer to define whether this particular buckling factor is going to be useful or not. So for example, in our case, let us say always if the load is applied only in this particular direction and I don't have any change in the load direction, then I can just ignore these 2 buckling factors or load multipliers, and I can directly go to this particular mode and I can see whether it is going to buckle or not. Likewise, if I say there is a reversal of the load direction, then I need to consider this particular load multiplier as well. So depending on the type of problem, depending on your situation, you are going to select whether you are going to take up this negative buckling factors or not. And remember, negative buckling factors are not bad. They are always possible. You want to find out the buckling mode of this crankshaft as well. So what I am going to do is, I am going to just select every buckling load multiplier, and I am going to just right click, say create more shape results. And once I click on create more shape results, I am going to get this in the form of deformations inside the solutions branch. What I am going to do is, I am going to right click, say evaluate all results. And once I evaluate all results, here in the graph area, see, this is going to represent the buckling load factor values. So as the load factor values, first two load factor values are negative, it is showing it on the downside of the axis, and these two are on the upper side of this axis. So if I click on the total deformation one, I can find out in this particular mode, this is going to take this particular shape. Remember one thing, whatever the values you are going to get from linear buckling analysis, we have to make sense of only the load multiplier as well as this shape. You cannot find out the direction of buckling using this linear buckling analysis accurately. In order to find out the direction in which this particular structure is going to buckle, you need to be going to non-linear buckling analysis, in which you are going to use the large deflection theory as well as incremental steps of load will be applied to characterize the behavior. But this particular linear buckling analysis is important to find out the buckling load factor and to estimate whether this particular structure is going to work or not. So I can just click on any of these particular modes, and I can just animate those modes and say in which shape it is going to buckle. So once I've done all these things, I'm also going to check whether this particular object is going to fail under static conditions. So what happens, I'm going to just right click, I'm just going to right click, say insert, go to stresses, go to equivalent stresses, and I'm going to just right click, say evaluate all stresses. So once I evaluate the stresses are around 383, but the material can withstand a load of up to 3E7 psi. So we can say that this particular body is not going to fail due to the static conditions. So this is how you can perform buckling analysis using Ansys Workbench. In the next lecture, you are going to see how to perform a thermal buckling analysis on a bimorph using Ansys Workbench.